today's video, we are going to create experiment 5. So, we will create a half-wave rectifier with RC load. So first, we should place our components. The project is already made like we did on last experiments. So first, we will have an AC source or the sine wave source here, which is the voltage source, and sine here, and then we will place a diode since it is a half-wave rectifier, and then uh, we will place a capacitor here, and lastly the resistor there. So we should rotate this first. We should rotate uh, our capacitor and the resistor. Oops, sorry. Uh, Wait, I double click it already. Here, rotate, there. So, as we can see, when it comes to an RC load, the parallel and the resistor should, eh, the capacitor and the resistor should be connected in parallel. So, and don't forget always the ground way. To enable the ground, press G and then click OK here. So now we would connect all of the components here. So wait. So you should try to uh, do more rounds since sometimes the wires overlap. So you should connect the joint one at a time. But let's okay. So I think there is no problems with this. Now we will set the values for the capacitor, resistor, and the voltage source. Since for the diode, it should be by default or the D break. So for the capacitor, it should be set on 100 microfarads. And then for the resistor, it has the value of 2 ohms. And for the voltage source, V off is equals to 0. Okay. The amplitude is 220 volts VRMM. Like the last time, we will use curly braces. Then 220 times square root of 2. Then curly braces enable to convert 220 VRMS or the effective value of the voltage of 220 into its maximum value or the peak current. So now we will click OK. Then the frequency is 60 hertz, and the value of AC is 0. So uh, everything is set. Then we will create a simulation profile for this circuit. So go to PSpice, new simulation profile, and we will name it Experiment 5. Then click Create. And now we have a dialog box. So as the same always, so we will uh, set the runtime to 1 cycle or 16.67 milliseconds, and its maximum step size to 10 microseconds. Then click OK. Now we will try to run our simulation. Uh, the run PSpice, and there's a new tab. So and here is the simulation space for the circuit. So since we are going to measure an angle, so we will uh, right click the plot, then uh, wait, so we will go to plot, then axis settings, and then axis variable. So this we will edit the trace expression. We will use a time times 60 times 360. Then click OK, and then click OK again. So now, even though there is an S on each number, this will register as a uh, ang as an angle. So now we will add the traces. So for this experiment, we will use the RVR1 colon 2, which is here. As you can see, it is the angle of a uh, sine half wave rectifier, and then we will add another trace, which is the VV1 plus, to demonstrate the input. So as we can see, uh, the graphs are almost similar, and there's a little space of curve here, which the angle still conducting, and then it flats. So we will try to measure its theta. So we will adjust the cursor to its intersection point. So as we can see, its intersection point is here. So as we can see, uh, the conduction point for the circuit with a resistive load of 2 ohms, it is 170.227 or 170.227 degrees as we measured here. So for its VO max, as stated here, it is 50 point 50.0 846 volts. So we will try to add another cursor here. Let's try. So first we will adjust here, and we will look the angle before it uh, reaches 0. So let's see. So you can see the VO max is 50.846 and its VO mean is 0. No, no, it is 3.80. So our VO mean is approximately 0 since it is a control wave it is a half wave rectifier. So the delta VO trying to subtract 50.846 to 0, it's still 50.846. When we try to measure the current of ID peak or the current of the diode with its peak, we will add we will try we will delete the traces first to avoid confusion, then add trace which is ID1. So as we can see, it is a half-wave rectifier, the waveform of a half-wave rectifier, and we will try to measure its peak. So as we can see, its peak reaches 148.101 amperes. So that is the peak of the current of the diode. And now we will try uh, to measure the peak of the capacitance. So add trace, then IC1, then click OK. So as you can see, it is unstable. So we will try to measure its peak. It's around 11.153 amperes. Let's try another trace to have an accurate measurement. See this one. Let's try. So it's the same, but by trying to measure its peak, it still says that it is around 11 amperes, which it has only difference of el- uh, around 48 point 048 amperes than the previous one, but still it is approximately equal to 11 amps, measuring its the current of the capacitance. So we will measure the average values and uh, power and RMS values of some components. So first we will start the average value of the diode current. So we will add traces again. So add trace, then average, and then ID1. So click OK. So now by measuring its average value, so the average value for the diode is 47.001 uh, amperes, or approximately 47 amps. So this is the average value of the average current of the diode. So next, let's delete this first. Let's add the trace of the RMS value of the the current of the capacitance. So we will search for RMS here. Wait, there's an error. Then we will select IC1, and here, this is the RMS, the waveform of the RMS value of IC1. Then measuring it, the RMS value is around 5.5027 amps, or around 5.5 amperes. That is the the RMS current or effective current of the capacitance on our circuit. So we will delete this trace to avoid confusion. So now we will measure the average value of the current across the resistance. So there, this is the waveform of the average value of the current in the resistance. So by measuring the average value of the resistance, it is about, as we can see, it's negative. So it seems that the polarity is reversed. So it is around, it is for negative 46.998 amperes, or around 47 amperes as the amperes. So the average current of the across the resistor is for this around 47 amperes. Let's try to measure the average power of this capacitor. Let's remove the traces first. Then we will try to measure its average power. So now, this is the graph of the uh, average power. So as we measure it, it is around 10.889 kilowatts. So the average power across the resistor is around uh, 10.9 kilowatts, or 10.889 kilowatts to be exact. So what is the average power of the voltage supply and across the diode? So first we will plot the average power of the supply. So let's remove the trace. Then we will go to average and then WV1. Okay, so there, as we can see, there is a negative power again. It seems the polarity is reversed. So by clicking the cursor, we can measure the power. So let's see. Okay, so the average power of the absorbed by the voltage supply is around 11.481 uh, kilowatts, or around 11.5 kilowatts, as we see on its measurement of, of the plot. So, and lastly, we will try to measure the average power of across absorbed by the diode. So let's see, average then the power. So as we can see, we can estimate it's around 0. Uh, around 600 watts, as we can guess, but let's try to measure to the exact value. So as we can see, the power abs- across the diode is 592.405 watts. So as we can see, it is almost close to 600 watts as we estimated earlier before we try to measure the power across this RC load. So as we can see, RC we can using the PSPICE simulation, we can able to measure the peak current, the angles, the angle of delay, or the angle of conduction for the uh, resistance for the circuit rather, and the average values like the average current, average power, and its RMS values. And also we seen earlier that we have produces negative values, as we suspect that there is a reverse in polarity connected in our circuit. Hope you like this video and see you again next time.